Yesterday, I gave you a graph that has force on the y-axis and time on the x-axis. There were three words that I told you should automatically come to your mind when you see this graph, regardless of the shape. What are those three words? Area equals impulse. Good. When you see this graph, there's a very good chance you're going to be asked to solve for impulse. If that's the case, then area equals impulse is going to tell you exactly how to solve for your answer. There is a chance that you're going to be asked to solve for something other than impulse. That's okay. I still want you to think area equals impulse, because even though that's not going to get you the full answer, it's going to help you, it's going to lead you to the full answer. So regardless of the shape, if it looks like this, or if it looks like the graph that we had yesterday, it doesn't matter. I want you to be thinking area equals impulse. Now, in this particular case, to find the area, we actually have to break it down into three sections. This section would be a triangle. And how would we find the area of that triangle? Base times height divided by 2, or 1/2 base times height. Good. This is a triangle as well. So 1/2 base times height again, or base times height divided by 2. What's this one? We'll call it a rectangle, though it kind of looks like a square. Okay, we'll call it a rectangle. And the area of a rectangle, or a square for that matter, is equal to what? Length times width, or base times height. When we calculate this area, it is the impulse, and this impulse will be a positive value. Why do you know it's a positive value? How do you know that? It's in the positive section of the graph, or it's above the x-axis. Good. Now, if we continue that on and drew a line like this below the x-axis, then we could find that area as well by using 1/2 base times height, and then length times width again, adding them up. But this one would be this one's positive, then this one's going to be a negative value. It's negative because it's below the x-axis. Now, add them all up. If the total area is positive, then you've got a gain of momentum. If the total area is negative, then you've got a loss of momentum. If you're asked to solve for impulse, you're done. If you're asked to solve for something else, like maybe the change in velocity, maybe the mass, or something like that, there's one more thing that we can do in addition to this thing that we always do. What is that other thing? I'll give you a little hint. It's an equation. Cody? Good. Almost, anyways. Impulse does not equal the mass times velocity. It's equal to mass times change in velocity. So be careful with that. A lot of times it's not going to matter. You'll get the right answer by just calling it m times v. But sometimes you'll mess up on that because you'll fail to take into account an initial and a final. So make sure when you're talking about momentum, it's mv. When you're talking about impulse, it's m times delta v. So you're always going to use this, always going to use this one, and then you're sometimes going to use this one depending upon what it is exactly that you're asked for. Good? All right, that's all I want to do with that today. We'll spend a little bit more time going over our homework on force versus time graphs tomorrow. Today, what I want to do is spend a little bit of time talking about some qualitative implications of impulse, which is going to lead us nicely into the activity that we're going to do in just a few moments here. The demonstration that we just did comes down to one fundamental concept, as well as all those other examples that I mentioned, like cradling a basketball or having your head hit an airbag versus your steering wheel. The one fundamental thing that this comes down to is what I call a predetermined impulse. When an object is stopping the impulse that it experiences, you guys remember what impulse is, right? Impulse is the change in momentum. The impulse, the change in momentum that that object experiences will be the same no matter what. This is a certainty. When you're driving down the highway in your car, there's a lot of things that we don't know. A lot of things that are going to happen in the future that we can't necessarily predict with any degree of certainty. But we can predict one of them with 100% certainty. You are moving down the highway at a certain speed with a certain mass, you will stop. You will eventually be stopped. And because of that, your impulse will be exactly the same. We can predict what your impulse is going to be, no matter how you stop. You can come to a gradual stop at a stoplight, or you can come to a crashing stop against a concrete wall. Your impulse will be the same. We know this with certainty. If my momentum is 100, and then sometime down the road it's 0 because I'm at rest, my impulse is negative 100. It doesn't matter how I stopped, my impulse is negative 100. Does that make sense? Well then, why is it that sometimes stopping your car hurts, like when you hit a concrete wall, and it sometimes doesn't hurt when you gradually stop? Well, it's like sometimes you jump off your desk and you bend your legs and it doesn't hurt, or you don't bend your legs and it does hurt. Here's the deal. When you have a predetermined impulse, which occurs when you're stopping an object, whether it be you or your car or the baseball, when you have a predetermined impulse, that symbol, by the way, just means it's not going up, not going down, it's not changing. You have a predetermined impulse. If I can increase the time that it takes to stop by bending my knees, by gradually putting my foot on the brake pedal versus hitting the concrete wall, by cradling the baseball as it's coming towards me, or the hockey puck, or the basketball, or whatever, if I can, by using an airbag to absorb the impact on my face or on my head when I'm in a car crash, if I can increase the stopping time and the impulse is going to stay the same, then the force must go down. It's not impulse that hurts, it's force that hurts. You're in an airplane traveling at 800 kilometers per hour in the sky. One thing you know for certain is the impulse that will be experienced by that airplane, because you know that airplane's going to stop. Now, odds are it's going to stop in a safe manner, but you don't know that for sure, right? It could come crashing down, but it's going to stop. The impulse is predetermined. We know what it's going to be. But if we can increase the time that it takes to stop, i.e. land pretty safely, then we can decrease the force and you don't get hurt. If we minimize the stopping time by crashing, then we maximize the force. Let me throw a couple of numbers in there just to maybe make a little bit more sense. Let's say the impulse is 10. Just pick a number. My time interval is 5 seconds. What would the force be? If my time was 5 and my impulse was 10, 2, my force would be 2 newtons. Okay? Let's say now I have the same impulse, the predetermined impulse, right? Now I'm going to increase the time to, I'm going to make it 10 seconds. Increase the time to 10 seconds. What's my force going to become? 1. Same impulse, because the object was stopping, I increase the time that it takes to stop, I decrease the force, less chance of injury. This is the basic principle behind anything that cushions an impact. At least it's one basic principle. There are sometimes more, but this is one principle that's always involved in impact cushioning things. This will be a question on your diploma exam. I don't know whether it's going to be an airbag, in the context of an airbag, or cradling a basketball, or jumping off of a desk and bending your knees. I have no idea what it's going to look like, but I can tell you it's almost certainly going to be there. The answer to that question is impulse is the same, time is bigger, force is smaller. Got it? Now, the other one, this is not what your activity today is based on, but we'll just finish this up and then tell you about the activity here. This is when we don't have a predetermined impulse. A predetermined impulse occurs when an object is stopping. When an object starts, the impulse is not predetermined at all. Usually what we want to do is maximize the amount of impulse and therefore make the object go faster. There's a golf ball sitting on a tee. There's a golfer here. Okay, there's a golf ball sitting on a tee. You know that to make that golf ball go farther, you need to make it go faster, right? What's one way that you can make that golf ball go faster? Hit it harder, right? Hit it harder. Why? Well, because if I increase the force, then what's going to happen to the impulse? As force goes up, impulse goes up. Impulse is not predetermined, I can change impulse. I can make impulse bigger or smaller depending upon what I do. It was predetermined when the object was stopping, but when I'm starting, I control what the impulse is. So I hit the ball hard, but that's not the only thing. Okay, lots of people really, really strong, okay, hit a ball really, really hard, but then the ball goes 12 yards. What do they need to do beyond hit the ball hard? Speed up the swing, hit it right, like good form, right? If you do it Happy Gilmore, then it's not going to go very far, right? But if you have good form, and I wouldn't pretend to have good form, but if you have good form, follow through, then the ball's going to go farther. Why? Because I maximize the time of contact between the club and the ball. More time of contact means more impulse. Got it? So when you have an object that's stopping, it's an interaction between F and T. T affects the value of F. But when we have an object that's starting, F will affect delta P, and T will also affect delta P.